I've been researching podcasts and podcast creation. This research actually began right before the Olympics. Hard to believe that that was also this year. So I was looking at sports podcasts and experimenting with the Dolby.io APIs. Now, these APIs include some media processing tools that can be pretty interesting data points, which of course, got my data science brain doing loops on like all the possibilities for some of the applications. And so I got pretty into the audio data space. I explored a lot of projects relating to podcasts, such as like ad insertion, like natural ad insertion in podcasts, which if we get some time, we'll chat about that later. And I'm hoping to share a few of my like takeaways, my gotchas, and learnings from this research with everybody here. But before we get on to that, like what exactly is audio data and why should you be interested in it? Well, sound as we perceive it is fundamentally just a series of vibrations passed through a medium and interpreted by an ear. You can hear me now because the speakers in your device compress air in such a way that you can interpret it. Of course, I'm not speaking in front of you in person, so between the step of projecting and interpreting these air vibrations is the computer, where audio is stored as a series of ones and zeros. And when converting these air vibrations to the zeros and ones, the computer needs to sample the air pressure at a repeated rate known as the sample rate, which is often 44.1 kilohertz or 44,100 samples per second. Additionally, the samples are taken at a resolution known as bit depth, or rather the number of bits stored per sample, which is commonly 16-bit. Hence, to store 1 second of audio at 44.1 kilohertz and 16-bit storage requires 44,100 times 16 times 1 second bits, or if converted, about 86 kilobytes. Additionally, most audio is 2 channels, which doubles this figure, and some mediums record audio at much higher sample rates and bit depths. Okay, though, who cares, right? Well, for comparison, a character, which is the amount of storage required to store just like one character, is only 8 bits. And that means to store my entire script for this presentation only requires about 2 kilobytes. So why is audio so much more storage intensive? It's because the recording is capturing much, much more than just the instrument or the voice speaking into the microphone. And the mistake lots of beginners make when analyzing, let's say, podcasts, you're doing a podcast project, is assuming that getting like a transcription, or rather just the words spoken in that audio, is like enough of the picture. And that's not to say transcriptions aren't useful. As we'll see later, transcriptions are like a great addition to your data set. But lots of tools or guides you find on the internet just convert the audio to text, perform the sentiment analysis on the text rather than the audio signals, and continue on that way. But obviously, like something is lost in this conversion and so much data is wasted. And this is the exciting part about audio data. It's such an incredibly rich data source with so much information captured that we're really only just beginning to utilize it in data science for what it's worth. And I like to describe audio data as like sneaky big data, because a lot of people, they don't see it taking up as much space as it actually does or being as information dense. So I like to joke that like sneaks up on you a little bit. Now, of course, your next question is, where can I find this data? If you go check out Dolby.io/awesome audio, we actually have a curated list of awesome audio technology resources for developers, including a list of data sets that you can use and the locations of where you can find audio samples. We also include stuff like social forums and networks for collaboration and contribution, educational resources, and some useful code samples. Now, everybody is welcome on this collection. So if you know any cool audio resources and want to make a contribution, please do. Absolutely, please share. Great. So now we know what this audio data is and where you can find it. So how do we use it? More specifically, how do we use it effectively? Well, I'm going to outline 3 tools and run through a notebook to show you so you can get a good look at how they work. And more specifically, I'm going to look at these tools on a collection of podcasts, which, as I mentioned earlier, has been part of my research with the company. Now, why did I choose podcasts? Well, podcasts provide an interesting mix of music and intros and outros. And it has a lot of speech, and the speech is sometimes split amongst multiple speakers at irregular intervals. Not to mention podcasts have like exploded in popularity over the last few years, with apps like Clubhouse routinely being, the top of the app store. Now, this podcast series we're going to explore consists of 20 episodes, each varying in length. In addition to getting the episodes, we also collected some supplementary data, such as like how many downloads each podcast got, as well as the dates that they were released. So I'm going to switch over to a notebook now. And please, by the way, I didn't mention this, if you guys have any questions or anything like that, drop them in the chat. I'll be pausing a few times throughout this to answer questions, and we'll also hopefully have some time at the end. Additionally, this notebook is actually available. I've got all the notebook stuff there. I couldn't provide the audio samples explicitly. However, here is the notebooks available if anybody wants to take a look at those. I'd recommend probably not following along for this presentation just because it takes a second to find the audio samples and a few minutes to install some dependencies. But if you're interested in tinkering around with it after the presentation, the GitHub link is right there. So great. So I'm going to start in my analysis notebook. So we're going to begin with every data scientist's favorite part of starting a project, which is getting all the dependencies and imports to work. Now, I'm hoping everybody here probably recognizes a few of these tools in the basic imports, things like matplotlib for plotting, pandas, numpy. In matplotlib, I like using 538 style for presentations. I think it comes out a bit clearer. We also include some NLTK dependencies. If you haven't worked with the natural language toolkit before, please don't be intimidated by all these imports. We'll kind of get on and have a chance to talk about them later, as well as some stuff from PyAudio analysis, which is another package that we're going to be looking at. But to begin, I kind of just want to look at like this basic data that we collected in conjunction to the audio samples. So the first thing I want to explore is we have 20 episodes in this podcast series. How many downloads are each episode getting, and can we see any trends? And the first visualization I have here is exactly that, the downloads per episode. And we can see that like episode 1 started out pretty strong, then kind of dropped down a little bit before having a sudden and rapid spike in popularity for episode 12. And then after episode 12, it drops back down again, but it drops back down at a bit of a higher level than began at. And already like this kind of raises an interesting question, like what was so successful about episode 12? And why was there such a spike here? Why did the viewership drop, after episode 1? Was it not to the expectations of the viewers? It's already some interesting questions. And we can also look at the minutes per episode, because maybe episode 12 is just like a 2-minute snippet, but it's actually not. It's actually the longest episode in the series. So something they did in this episode turned out really right. And that's interesting to think about. We can also see that episode 1 was the shortest, and from there they've kind of been getting progressively longer in duration with some spikes, which is pretty interesting. So that's kind of like our basic data. Again, if anybody has any questions, please drop them in the chat. But this is kind of like you're scraping your data. This is the basic stuff you get. And let's get a little bit more advanced here. So as I mentioned before, just looking at transcriptions misses a lot of the picture, but transcriptions and natural language processing are great to supplement the data set. So we're going to have a look at the transcriptions. Now, transcriptions are really good. If you guys don't know what transcriptions are, it's pretty much converting the spoken words in a podcast to text. Now, transcriptions are really great for stuff like content analysis. What are they talking about in these podcasts? Sentiment analysis, are they speaking favorably or disfavorably about certain topics? And classification tasks like, can we start grouping podcasts based on certain things that they're saying in them? Now I've included a transcription notebook. For me, I got my transcriptions using Azure Cognitive Speech to Text Services Speech to Text. If you don't mind muting, I'd really appreciate that. Yeah, Azure Cognitive Services Speech to Text Services, which has worked well for me. To use that transcription service, you provide an API key, you store your files on the blob and provide a pre-signed URL. And then you provide a pre-signed URL for the output container. Now, again, there's like a ton of transcription services out there. This is what worked well for me using their REST API. Of course, this one does cost though. So if you're looking for a free option, another one I was experimenting with is Pocket Sphinx, which is a free alternative. It's not going to be quite as accurate as speech to text, but it is free and it does run locally. And running locally, if you're analyzing some podcasts that are like an hour and a half long, it can also tie up your computer for a little while. So it's a good thing to consider. But yeah, included in the notebook is just some code in case you want to generate these transcriptions yourself. Cool. So what we're going to do, and actually I'll show the output of the transcription so you can kind of see what that looks like from Azure Cognitive Services. They output in a JSON and they give you some basic metadata, like the duration of the audio file and stuff like that. Then they provide a lexical, which is all of the spoken words in order, as well as including like a couple of different models, like a display, which includes all the punctuation. And most interesting, I think, or most useful, is they also include the sentences transcribed at certain kinds of timestamps, which is very useful for keeping track of like which part in the podcast they're talking about various things, as well as confidence ranges and a few different models. So I like Azure speech to text. It gives you a few different options to play with. Yeah, that's kind of the gist of that. So what we're going to do is we're going to start by loading in these transcriptions. We're only going to worry about the lexical for the moment, just because we're just beginning with some really basic transcription analysis. And we're going to count out the total words in each podcast. So interesting, again, 20 episodes, starting at 50,000 words all the way up to 90,000 words. Here is the word count by episode. And already some of the interesting stuff to have a look at here is like episode 19, despite being shorter than episode 12, not much shorter, but it is shorter, does have like a significant amount more spoken words, which is interesting to think about. Maybe they had some people on that podcast that talked really quickly and were able to pack in a lot more words, or maybe the opposite is true for episode 12. So it's interesting to look at that, but I think we're probably more interested in the number of unique words each podcast presents. And again, we see episode 12 kind of shoots up there. It's the longest one. It makes sense that they'd have the most unique words. And it's interesting though, for like episode 19, how there's that like decrease in word or that increase in word count, but decrease in unique words. Are they maybe like repeating a few points or hammering some particular topics home that they just like do it again and again? It's interesting stuff to think about. Now let's break out into the first episode. Now what I'm doing here is I'm taking the first episode and I'm having a look at the most common words in that first episode. Now how this works is with the word tokenize package in the natural language toolkit, which splits all of the words out into individual entities. And then we can call frequency distribution on that, which pretty much just counts everything, right? If we plot it out, we can have a look at podcast 1 and we can have a look at the most common words that have been used and how often they've been used. And in this case, it's pretty standard. It's kind of what you expect. It's like a lot of joining words or connecting words or just like stopping words, things like I, the, like, you, and they. So this doesn't necessarily tell us a ton, But I think it's interesting that we pull out some words like think or like know. You can tell that maybe perhaps they're making predictions in this podcast, and there's some interesting stuff there. Now, if we filter out the common English stopping words are kind of just these words that we talked about here that maybe don't add much to the overall context of the podcast, but are picked up in transcriptions. So we can filter those words out by using a list of English stopping words, which we downloaded and imported before. And from here, what we can do is we can then calculate a frequency distribution for the most common words once we've filtered out the stopping words. And this is good because we get a bit better of a picture of the like the content or what they're talking about in this like first episode of the podcast. Again, you see some stuff that isn't super telling, like and not and are and no, but you do see some other points such as like team, game, 3, 4, 2, 5, 20. And this maybe gives you a bit of a hint as to what kind of sports podcast we're looking at here. Ones where scores of things like 3 are, pretty common, and a team game. Some interesting stuff here. And if you know your American sports, you probably already have an idea of kind of what sports this podcast talks about. But interesting to see that in a scenario where we're not listening to this whole podcast, we can actually start to draw out some of this meaning.
Braden, sorry to interrupt you. There's one requirement from one of the participants. He's asking if it's possible to zoom in to visualize it a little bit bigger, maybe. I'm not sure if that's the inquiry.
Yeah, thank you for mentioning that. Does this look a little bit better?
I think we can appreciate it well. What do you think about it, Tom? Can you appreciate it better?
Yeah, if people just want to throw some messages in chat, I can play around with this a little bit and get the view a bit better.
All right, so Eyal is thanking very much for the 548 styles and the mention of the ads, your coding. And some was also asking about the common format for the transcribed audio. The only issue is that I do not fully know which format he was specifying.
Well, maybe I'll jump back and answer a few of those earlier questions in a second, but it looks like they're happy with the size of the code for the moment. So that's great. Thank you for stopping me on that. But assuming this is all good, and it looks like it is, I can keep going. So one of the really cool things that you can do with transcriptions is you can do some basic sentiment analysis. Now for me, I'm just using Vader, Valiance-Aware Dictionary for Sentiment Reasoning, which is the lexical approach to sentiment analysis. And what it does is it pretty much just assigns words certain positive, negative, or neutral scores. Like the word bad would get a higher negative score than the word great. It's a really basic approach to sentiment analysis. I think for the purpose of the analysis that I'm doing here, this is a great place to start. However, if anybody is interested in playing around with this, again, the notebooks are available. Please import some more advanced models and see if you can learn more about the sentiment analysis. But for the purposes of this, it's pretty simple. And I'm just using a pre-trained model provided in the natural language toolkit. So I haven't even trained it specific to podcasts. Now, for this episode 1 right here, we can have a look at the distribution of sentiment throughout the first podcast. And this is pretty interesting at a baseline. We can see that, all right, like there's a little bit of negative sentiment, majority's neutral, which makes sense if we go back up to, our most common words and we see things like the and like. Those words don't really carry a sentiment with it. So it makes sense that we're getting a pretty high neutral score. What I think is more interesting is the fact that on average, we're getting a little bit more positive sentiment than we are getting negative sentiment. And this, of course, depends on the model that we're using. In this case, we're using a pretty basic one, so it's not very context aware. It's maybe not picking up on things like sarcasm. But for the moment, we'll just assume that this podcast is kind of more positive than negative. And so this is for podcast 1 here, the first episode. Now let's break it out and let's see if we can calculate this stuff for all of the podcasts to kind of get a bit of a better picture of like how sentiment changes across the notebook. So we're calculating out the sentiment by each of the podcasts that we present. And we can see here, we've got the negative sentiment in red, the positive sentiment in green, and the neutral in gray. And these are each of the episodes 1 through 20. And this is kind of like the percentage composition if we get this sentiment across the entire transcription. And there's a few interesting things that we're seeing here. We can see like episode 5 really goes hard on the negative sentiment compared to like a lot of the other episodes. And I think that's really interesting, especially if we scroll back up and have a look at the downloads per episode. We can actually see episode 5 was not one of their most popular episodes. And in fact, the following episode after that was really, really unpopular. So perhaps the popularity of the episode, or in fact, how negative episode 5 was, might have contributed to how episode 6, wasn't that great or wasn't that well received. We also see our most popular episode, episode 12, kind of has the least amount of neutral sentiment in it. In fact, it's more positive and more negative, which suggests that maybe in this podcast, they're talking about some more polarizing topics. There's maybe a bit more debate. It was maybe a bit more like emotive and energized, which might have been why it was like a breakout episode for him, why it maybe had some viral features to it, because, it was taking a different stance on some of the things that they're saying, which is pretty interesting. I think it's important to calculate the average out across the whole series, and we'll see why later on. We can see that on average, the series is a little bit more positive than it is negative, but overwhelmingly neutral. And we'll return back to these values a little bit later as we kind of do some more in-depth analysis. But what we can do is we can also load in the first podcast again. And specifically, we can calculate out the change in sentiment by sentences. So in the first podcast, they have 1,200 sentences in it. And if we look at just the first sentence to the 10th sentence, we kind of get a bit of a plot that looks like this. So this is the aggregated sentiment score, or as the sentiment score gets added over time to contribute to the overall sentiment. And this is the breakdown for just the first 10 sentences. And it's interesting to see that in the first couple, not predominantly positive, it's definitely a little negative. But over time, the positive sentiment begins to overtake the negative sentiment present. And this, becomes more pronounced as we scale out the boundaries. So if we look at like 100 sentences, for example, we can see this separation really just starts to grow. And now at this point, red is not catching up to green, and green's absolutely not catching up to neutral. And we have 1,200 sentences. So if we bump this up to, 1,000, we can see these lines really begin to straighten out. Now there are 1,200 sentences. So if we instead specify the range to be, let's look at the last 50 sentences here of the podcast. This is another interesting thing to kind of see. You can see that in the last 50 sentences, the negative or the aggregated negative sentiment tends to flatline, especially when compared to the positive sentiment, which grows. And in the context of podcasts, this makes sense, right? Like, you want to leave your viewers on a high note. You want to leave on a positive note. Like, thanks for watching. Really appreciate you guys watching our podcast or listening to our podcast. And again, it's just interesting to see that reflected in the data. Now, before we jump onto the next tool, let me have a look at a couple of questions in here. If you have any more questions, please feel free to drop them in the chat.
All right. So we are going to follow up the questions at this moment. One question comes from Jim. He's asking about the rough costing time and money for Azure to transcribe an hour-long podcast. Yeah.
Yeah,
So,
well, that's a great question. So there's two costs you actually have to factor in for Azure. You have to factor in the blob storage as well if you're storing this stuff on the cloud. If I recall correctly, signing up for an Azure account for the first 12 months, you get like $200 worth of credit. So storing it on the cloud, if you're not storing like an insane amount of data, that should cover out there. But if you want to use cognitive services, it doesn't cost from the 200 that you get when you sign up for the account. You have to put in extra money. I think to transcribe about an hour and a half long podcast just using speech to text, it was about like 20 cents ish. But that's also because we're doing the most expensive kind of transcription, which is the one that does every single model that they have, so that I can then take and compare them. You could instead pick out the model that works best for the particular language that your audio is in, and I don't know if people have accents or whatever, some models work better than others. And that, if you focus in on just using one model, that might bring the cost down substantially.
all right. There's another question from Tom. He's asking this. Could you simply extract unique identifiers that correspond to real-life objects and correlate with frequency of mentions on Twitter? Then you would know if the episode was on popular subject.
Yeah, and that's a really good point. If we want to supplement the performance of the podcast with, say, like some social media scraping to see where and when people are mentioning it, that would be a really great idea. And you'll actually see later on, we do some stuff where we pull out like specific organization names and specific like nouns from the text that we've transcribed. And I imagine it'd be something pretty similar if you want to do it in terms of scraping on social media. And I think that's all the questions. So I'm going to proceed. So the next package that we're going to look at, and we'll kind of come back to these as we go on, is PyAudio Analysis. Now, PyAudio Analysis is an open source package by Theodoros Giganopoulos, who is a principal researcher of multimodal machine learning at the Multimedia Analysis Group. Now, this is an open source package. I'll drop it in chat in case anybody wants to take a look. But it includes some really quite cool and useful stuff that you can do on the actual signals in the audio data. So we've started by generating these transcripts. Well, now let's go a bit deeper and let's see what we can learn from the signals specifically. And they do stuff like feature extraction, classification and regression, segmentation, some data visualization stuff, which I really like, as well as some other functions like transcoding. So I really like this package for stuff like exploratory data analysis, EDA. Because of those visualization packages, it lets you get working on the signals really quickly without having to think about, potentially messing around with some matplotlib stuff or anything like that. It's really good at creating features for data sets based off of the signals, which in turn is really useful for clustering and classification applications. Now for this, I'm going to switch back to the default style of plotting just because it renders a little bit better if we just stick to the basic matplotlib style guide. And also what I'm going to do is I'm going to trim out 20-minute snippets of the audio rather than do the whole podcast. And this is just because this package does a lot of calculations and it can be quite, it can take a long time to run. So we're going to trim those out for our sports podcasts. And we're also going to pull in some business podcasts so we can do a bit of a compare and contrast. So while that's running, I'll go talk a little bit more about the package. Now, the feature extraction model is really interesting, and we'll get on to what a few of these mean. But what it pretty much does is it takes the signals in the audio and converts them into 34 different features based on like windows of time that you want to look at. And if you have 2-channel audio, this doubles. So what it's doing is it's creating these like 64 length vectors, because we do have 2 channels of audio in this case, creating these 64 length vectors of features for things like energy, zero crossing rate, which we'll talk about a little bit more here. Now, zero crossing rate is the rate at which a signal changes from positive to 0 to negative, and from negative to 0 to positive. So you imagine this as the rate at which a signal flips its polarity. And energy, another term that's kind of worth knowing, is the sum of the squares of signal values normalized by the respective frame length. Now, that's a kind of complex explanation there, but you can pretty much just imagine it as a measure of signal strength. Now, full disclosure, I am not like a signal engineer. A lot of this stuff I've just kind of learned working with audio data. So, you know, it is stuff that you can pick up if you're a first-time user. Please don't be intimidated by all this crazy technology. But also, like, I might make a couple of mistakes. So please let me know if you do know about this stuff. But what we're going to do here is we're going to look at the zero crossing rate and energy for our first sports podcast trimming. So the 20-minute trim of our first sports podcast. And we're going to use a function provided in the kit called feature extraction. Now we're going to narrow down to just 1 channel of audio for this feature extraction, and we're going to specify a window and a frame. Now, the interesting thing about all these values is you can calculate them for any length of audio. Like, we can take an hour and a half of audio and calculate a zero crossing rate. The problem is that over long durations, it kind of just like averages out to a mean. It doesn't really tell you much about specific segments. So here we specify a window and we specify a frame. Now, the window is like the amount of time that it's looking at, and the frame is like the calculations that it's making within those windows. So it's going to make 2 calculations for each frame. The frame length is of 0.05 seconds. So it's a pretty small frame, and we're going to do that for 20 minutes. And if we do that for 20 minutes, it takes a second to run. You can imagine how long it'd take to run for the full length of the podcast. And we get output 2 graphs here with their data visualization package, the zero crossing rate and the energy. Now, on their own, these terms are like fairly abstracted from what we understand like noise to be. So it's really hard to look at these graphs in isolation and go, all right, like, cool, like I can see that this is a sports podcast, you know. But where it does get useful is if we then run the same function for our first business podcast, is a 20-minute trim of that, and compare and contrast. Because again, in isolation, we can't really understand as well what we're looking at. However, if we contrast it then to like a business podcast, we can kind of see how these values are denoting some kind of separation in the underlying signal of the audio. Few things to note here is that this zero crossing rate is on a scale up to 0.5, and this energy is on a scale up to 0.3. And now these are the plots for our business, for one of our first business podcasts. And we can already see, like, wow, the energy, for example, is way lower. Scale only goes up to 0.14, whereas up here you can see it's all the way up to 0.3. There's definitely like a lot of difference in the spikes of intensity in signal in the sports podcast than the spikes of intensity in the business podcast. It's a bit harder to see this with the zero crossing rate, but again, you can see that it's probably on average just a little bit lower than the zero crossing rate for sports podcasts, with a few more spikes up here. Now we're going to return back to this in a second, but let's have a look at a few of the other visualization stuff. So we can generate chromograms. Now, a chromogram is a transformation of a signal's time frequency properties into temporally varying precursors of pitch. Now, what that's a fancy way of saying is that we have like all of this cool signal data, but there's a huge range of like signal that falls outside of human comprehension because of our ears. So what we can do is we can plot a chromogram, which kind of takes that signal and it plots it along a scale that people might be a little bit more familiar with, which is like a music scale, right? A all the way up to G sharp. Now, chromograms are typically more useful for things like music, but it's kind of interesting to see that one, the package includes this stuff, and two, the differences between this is the business podcast here, and this is the sports podcast here. And if we actually change the boundaries of this out a little bit, so that's just 3 seconds. If we look at it like on a scale of like 100 seconds, you can see some more concrete patterns form. So again, in our sports podcast, we can see high concentrations of action at G, at D, at B, and at A. Whereas for our business podcast, it's definitely like a lot stronger at A and B, D, F, and G. You can kind of see these highlighted segments where the brighter the individual segment part in there, the more intense the audio is for that part. Now, this is just some basic visualization stuff. I'm just kind of showing you with the package. What I find is really useful is the feature extraction function. I'm not going to run this because it takes a second, but what it does is it creates vectors of all of these different features for each channel. And what that ends up looking like is we get these really big CSV files and NumPy arrays of like vectors of features that are present in the audio. And let me just get up an example for you here. Yeah, we've got this example. And you can see what this kind of looks like in a CSV. It's just these huge vectors of numbers. And again, we specified frame length. In this case, I specified a bit bigger of a frame length, so it'd run a bit quicker. But you can see, all right, here are all of our features, up to about 60 for our 2 channels, and then across all of these different columns. So again, this is like fairly abstracted for us humans. We can't like look at all these numbers and really understand what's going on. But what it's really useful for is feature like clustering and visualization. So this package includes another function which you can run. I'm not going to run it because it takes a second, but I ran it before. And what it pretty much does is it uses these big CSVs to actually generate some like clustering and to try and split our audio samples up into groups. So, and it outputs it in a really cool visualization in HTML. But you can see we had 10 business podcasts and 20 sports podcasts. And what it's done is it's used the features in these matrices to, one, cluster them into separate groups, which is what we get here. These are all of our business podcasts in blue, and these are all of our sports podcasts in red, sports being 1 to 20 and business being 21 to 30. As well as pulling out some of the signal-based connections between these audio snippets. So you can see here, for example, episode 1 shares some kind of signal-based connection with episode 3, 5, 6, and 7, whereas episode 20 really only has one connection, which is to episode 12. And we see this in the business podcasts as well. 21 connects to like almost all of the other podcasts, but like 22, 24, and 25 kind of don't find any matches. And this is a limitation of the data set. We only have 10 examples or 30 examples total, but 10 examples where they might share a connection. And you can see for these ones here, some of those connections are found later on. Now, what these connections are fundamentally is like, we've got all of this signal data. We have these huge feature vectors. It's just able to pull out like some of the reoccurring themes between these audio samples. And if we plot out some of these features individually, let's actually start with the first metric, which is energy. Now, if we plot out energy, here again, we have our business podcasts, and here we have our sports podcasts. You can see that like just in this signal, there is like some separation between like business podcasts, which have been mastered a certain way, and sports podcasts, which have been mastered a different way. And this might be because, you know, of the microphones that they're recording on, or it might be because they have access to some kind of audio engineer who's able to, you know, correct the audio a little bit better. And it's interesting to see that this plays out so much. And we can have a look at a few different other metrics. This is the zero crossing rate, which we talked about. Not as much difference. You can see a little difference, an interesting spike there. We can look at like some of the other features. Again, we have a whole heap to play with here. And you can kind of see some differences and begin to understand like, okay, this is how like it's able to cluster these a certain way, is that obviously in these underlying calculations that it can make on the signal, it's able to find some differences. And that's why I really like this package as kind of like a first pass. You're starting on an audio project. You have a bunch of audio samples. You don't really know much about them. This is a really good place to start because you can just go and find some more natural clusters and break them out into some groups and see if you can actually identify some patterns in the signal, which is pretty interesting. Now, again, I'm going to pause for a second and get some questions if anybody has any questions.
Braden, there's a first question from Tom. So he's asking, it would make sense to line it up with transcribed text, so the energy is on per sentence basis. You could analyze how specific words are stressed, perhaps? Could you analyze how specific words are stressed?
Yeah, absolutely. And that's actually another great idea. So if we go back up and have a look at our definition for zero crossing rate, for example, we actually see that it's pretty commonly used in things like speech recognition and music information retrieval. And this is because this zero crossing rate feature, when you do line it up with certain words, does help like indicate which word that person might have said. Along with all the other features, you absolutely can line it up, yeah.
All right, there's another question from E. Alcazin. He says, hey, nice visualization. What is the name of this type of plotting?
Yeah, so I think it is called a core dial. I'm not 100% sure on that, but that's what the package calls it, a core dial, which I guess kind of makes sense when you look at it. It does kind of look like a bit of a dial, but yeah.
Okay, thanks.
All right, so there are no more questions by now, so I think we can continue on, Braden.
Great, yeah. So for our next package, we're going to be looking at some Dolby I/O stuff. Now, Dolby I/O has a bunch of different media processing APIs. I want to focus specifically on analyze and analyze speech. Now, these two APIs are great for generating data from audio files, specifically for stuff like content structure and composition, speaker diarization. It also helps with like better content creation by providing features related to the quality of the audio and stuff like that. So if we want to use these APIs, I have another notebook over here for generating a data set using the APIs. You will need an API key, which means you've got to sign up for an account for our stuff if you want to use it. But we specify our API key, we specify the in path for where all this audio is, and then we specify two out paths. And the reason we have two out paths is, again, because we're using two separate APIs. We're using an analyze audio, and we're using an analyze speech API. Now, the first thing to do when using these APIs is we want to upload these files to Dolby Cloud Storage. And this, like once it's up on the cloud storage, we can then run our APIs on it. But you don't have to use Dolby Cloud Storage specifically. You can use any cloud storage. You can use like S3, you can use Azure, you can use Google. So what this code does is it just takes a whole directory of files and uploads them. And then you start analyze jobs, or you initialize a bunch of analyze jobs on it. And we do this by specifying the URL that we want to send the request to, media analyze. We specify our header. We define a body with the input of the file, as well as like what our output's going to look like. It's going to be an output in JSON, and we send up these jobs. Now, hour-and-a-half long podcast, it does take a little while to run. So what this script here does is it then just like queries the server, and when the files are done, it just downloads them back. Now the analyze audio results, I can pull it up and show you what these files kind of look like. The output is in JSON format, and we can have a look at some of the information that's contained. So we get some basic metadata about the audio, durations, bit rates, stuff like that. And then it breaks it out by process region and generates like loudness readings for every like segment throughout the podcast. It also gets us some interesting information, such as the signal to noise ratio, music, and the percentage of music in the podcast, speech, silence. And in this API, it actually breaks the silence out into particular segments that are timestamped. So you can flag them in the audio, go check these segments, and all right, we've got silence here. We can remove silence from this section. Silence is an audio defect, just as like the name describes. Like if you have a portion of your hour-long podcast that's like 2 seconds of just like no signal reading, even though it might not be the biggest deal, that is like a kind of a waste of space when storing the file. And it can provide a bit of a strange experience for users. If you're just listening to a podcast and there's a couple seconds of silence in there, you may as well just get rid of it. And silence isn't like a pause, like when somebody's talking and there's a pause. Like a silence is like an awkwardly long period of time where there's just like nothing happening in the audio. So being able to flag those out is really useful. And then the other API we use is the analyze speech. And same thing, we upload those files, then we start a bunch of analyze speech jobs, query for when those jobs are done, and download them. And the output of the analyze speech API is really interesting. Again, we get our metadata, but now it starts to break out things like the number of speakers, the percentage of talking that goes on. And then it takes these speakers and it breaks out specific points when they're speaking. So we can see like talker 1, he jumps in at section 1 here, which starts about 6 seconds in, and he speaks for 2 seconds. This is like right at the very beginning. So it's likely, him just saying like, hi, I'm a guest on this podcast or something. And it breaks it out for every single talker in it. So you can see these files are really big. It also includes stuff like a quality score and loudness readings. Quality scores are really good because if you have like multiple speakers on this podcast and maybe using different microphones or ones like calling in, their audio quality might be lower, might be better. And it's interesting to kind of look at like how that can change. And if you're like an audio engineer, maybe you can go in and correct it for that specific speaker. Now I see somebody's got a question.
Yeah.
Terrible
Actually,
name pronunciations. Yeah.
Yeah. Sorry. Sorry, Marcelo. I'll just ask for myself. So is the speaker, is that metadata that's given, or is it something that was inferred?
Like all of this data is just inferred from the audio file. I mean, things like the codec that it was uploaded in, MP3. I don't specifically know the inner workings of the engineering, but everything else is just inferred specifically from the signal itself.
So the fact that it says number of speaker talkers is 6, there might be a mistake, might be even 8, or it might be actually 4, but this is what it inferred 6 people.
Yeah, exactly. It inferred that it is 6 people. And what we can sometimes see, especially in the podcast space, is if they play like a clip of audio, for example, like, 5 minutes, they're talking about, whoa, this is a video that I saw the other day, and they play that, the algorithm does pick up the fact that like there are speakers in that audio segment that they're playing, which gets added to the data set, even though those people might not have literally been in the room where they're doing the podcast. Does that make sense?
Yeah, that's pretty cool. I'm just imagining, like, let's say you have an impersonator, right? You have like a comedian on, then it might identify the different impersonations as different people, potentially.
Yeah, no, absolutely. Also, if like, people did like accents and stuff like that, or spoke different languages, it can do that stuff. But yeah, that's our analyze API. So we get output in a bunch of these JSONs, and what we can do is we can load them in. I really like using pandas for this task. Now, when loading it in pandas, I recommend using the JSON normalize because we have some heavily structured JSON data. And I also recommend using a max level of 7 if you're going for stuff that has like between like 5 and 20 speakers, which some of our podcasts do have. And we can look at this flattened out. We get a bunch of different data here, some interesting stuff, the signal to noise ratio, the noise level, music percentage. When we get to those silent segments that I was talking about in the analyze audio before, flattening that out into a data frame is hard, and it wastes like a lot of data because you're just repeating a ton of stuff over again. So I actually keep that just stored in there in its normal form. And the first thing I want to do actually with these files is I want to break out and have a look at the composition of each podcast to see if we can learn a little bit more about the podcast. So again, we have our 20 sports episodes, and this is the composition. Speech in blue, this makes sense. It's a podcast. It's going to have a ton of speech. Music in red, they likely have intro music and outro music, so that's getting picked up. And then silence. And again, silence is an audio defect. And especially if you look at it in the composition of the overall podcast, you can see some stuff like a lot of these examples, like that might be up to 5% silence, or like 5% of your total hour-and-a-half long podcast is just silent segments. Like, that's not great. Now, also the composition is greater than 100 in some cases because music and speech does overlap. And you can think about in the context of they're playing their intro music, and then as the intro music's fading out, they're jumping in and saying, hey, welcome to our podcast. So that's kind of interesting with the analyze audio. With the analyze speech, we do the same thing. We can load it in again. We actually have a few less columns this time because this picks up a bunch of extra data just about the audio in general. This is more focused on the speech. And again, we can see when it breaks it out by particular talkers, we keep it stored in that JSON format. So we can get our columns, we can kind of get the shape, 20 podcasts, 15 columns. Cool. Now I'm actually going to draw for this segment here, and I'm drawing with a mouse. So apologies if this looks terrible, but it's easier to explain if I draw it. Now, in the case of analyze speech, we have this like heavily structured JSON where we have, all right, this is podcast number 1. And in podcast number 1, we have speaker number 1, and we have like speaker number 2 and speaker number 3. And now speaker number 1, well, he speaks in like segment number 1. And speaker 2, they also speak in a segment, and speaker 3 also speaks in a segment 1, and then he also speaks in segment 2. Get the idea. There's a lot of like different layers to like how this data is structured. So it already poses a challenge for visualizing this data. And there's a lot of different ways you can think about how you might want to visualize data like this. One of the ways that I came up with is representing these podcasts actually as a matrice. So instead of keeping it in the structured JSON format, I represent a matrice where this is speaker 1, this is speaker 2, this is speaker 3, this is speaker 4. Now, let's say, for example, that our audio snippet that we've analyzed is only like 10 seconds long. So 1, 2, 3, 4, 5, 6, 7, so forth, right? So another way of representing this rather than in the structured form is like an is speaking notion, right? And the idea is that, all right, if speaker 1 is talking in second 1, we're going to set that value as equal to 1. And if he's talking in second 2, we're going to set that equal to 1 as well, in second 3. But maybe he stops talking in second 4. Well, we set that to 0. Now 2 isn't talking, so it's 0, 0, 0, and then they start talking. So you get the idea. What we're pretty much doing here is we're building like a matrix of is speaking, 1s and 0s. So we can track like who is speaking when. And that's what this code here does. What it does is it pretty much populates this vector called empty here. And I call it empty because people are more often not speaking than they are speaking. And we can use that matrix to then plot stuff. Now, what you're probably seeing here is already, well, that's a 3 and that's a 2. Those aren't 1s. And so what I've done here is I've actually overlaid all 20 podcasts into the same matrix so that we can get a look at the whole series of like how intense conversation is in certain segments, right? For example, in the like opening like 10 seconds, there's probably going to be a lot of times when speakers 1, 2, and 3 are talking. Let's have a look at like the probability of this. We fit this all into the same vector by setting the number of columns to be the length of the longest one. We can kind of see, yeah, we get these vectors, cool. But let's plot this out. So what we're doing is we're looking at a scope. We're looking at all 20 speakers. So across this whole series, there's 20 unique speakers total. And we're looking at the duration, right? So as we saw, the longest podcast about 6,300 seconds. Let's look at just the 6,000 seconds. And we get this visualization that's pretty interesting. It's like a concentration of speech. And we can see some patterns that make a ton of sense here, right? We can see that, speakers 0 through 5 are pretty regularly talking, in the first, opening 1,000 seconds of the podcast, right? But as we get into like these longer podcasts, you can see that drops off because this is usually just resigned to like episode 12, for example, which is the longest one. We can also see that like down here, we record there being 20 unique speakers, but we can see that some of those speakers really don't play much of a speaking role. And this might be because they played like a video in the podcast or played an audio clip in the podcast, or maybe they just had a guest on for a couple of questions. We can take like a closer look at this. If we narrow the scope down to just 100 seconds, you can see some segments here. It's like, wow, speaker 1 is typically speaking like across all 20 podcasts, like 35% of the time he's talking in this like segment here, which is pretty interesting. We can narrow down the scope of the speakers as well if we only want to just like look at like 4 of them, for example, and you kind of get this picture, which I think is an interesting way to visualize it. And we'll kind of come back to this as we all wrap it together to show how this can be useful in a real world case. But I actually want to go back to the slides really briefly here. Cool. All right. So just saw a ton of code and you've just seen all the tools that we're using. I now want to like push this idea or how you can use these tools onto everybody watching. So now that we've looked at our tools and we've seen some of the data that we can extract with them, I want to see what you guys can come up with. Now our APIs cost on like a per minute basis, but if you sign up for an account, you get like 200 free minutes a month, which is like great for testing the APIs. But say you want to do your own podcast project like I've done here, you're going to need more minutes. And that's why if you like navigate to the link on screen, and I'll post it in chat for a second, there's an option to fill out a form. And in this form, you can talk about like a cool idea that you want to use. And it can include our API. It can include a bunch of like the transcription stuff. And what we're going to do is we're going to pick out like 5 of our favorite ideas. And we're either going to do that like live, like at the end of this session, if we have enough time, or I'll do it after and we'll reach out via email. But you pick out like 5 of our favorite ideas, and we're going to credit you with an additional 300 minutes. So you'll have a total of 500 minutes, which is like a fair bit of like computation time. That's like enough to like look at a series of podcasts or something. And we'll credit those minutes to you so you can maybe go mess around and try to do your own analysis. We're also going to check back in to the form on November 8th to credit an additional 5 ideas with more minutes. And we're doing this just because like maybe you don't have an idea right now, but maybe you're thinking about it later today and you go, actually, that's a cool idea. I wonder if I can get some minutes to try that out. And we'll credit those minutes to you, or we'll credit to 5 today and 5 on November 8th. So if you want to win some minutes now, go fill out the form. We'll pick our 5 favorite ideas later today and another 5 ideas next week. Feel free to submit as many different ideas as you want. A cool kind of Halloween thought starter that might inspire you on a potential project is performing analyze on like some true crime podcasts to see if you can detect like the most dramatic part of the podcast. And this can kind of be done by like looking at stuff like the loudness, like, you know, maybe it's a group of them and they're reading scary stories and they all go, whoa, at one point, you know, and you can detect that as being a dramatic moment. Or you can look at like when people are talking and the relationships between talkers or speakers. There's a lot of different ways you can look at solving these problems and you can get creative with it. Now let me go share this link into the chat. Sweet. Oh, looks like I already shared it. So thank you. And I'm going to switch back to my notebook a little now. So cool. We've looked at all of these tools. And as I mentioned before, I was using these tools in the context of better understanding podcasts, coming up with some ideas. So let's kind of recap on a few of the things we looked at. We saw the views per episode. Cool. We got a spike at 12, right? We saw the composition of podcasts. And it's interesting to note, actually, that the quality or the number of speech defects in these podcasts actually improve as the podcast goes on. And this is like, you can see this kind of happens after like episode 12, it like decreases down a little bit. And this is interesting to think about, right? If we plot them out on the same graph, we can see the percentage of silence, which is an audio defect, and the number of downloads. And we can see after they have their huge spike in popularity at like episode 12, the number of audio defects decreases pretty dramatically, right? And this raises like an interesting question. Like, is there a relationship between episode 12 doing really well and their audio quality improving, you know? Did they get some success? And with that success, you know, they hired an audio engineer, or just because their podcast was seen by more people, somebody just complained about it enough and they're like, all right, we're going to fix it. And it's an interesting thing to think about in the context of the podcast. Now, one of the ideas I kind of had was, all right, well, like, let's learn a little bit more about episode 12. So again, we like tokenize out this stuff. We filter out all those stopping words. Like, what kind of words are we mentioning in here? Well, it's pretty standard stuff. It's kind of similar to what we saw in number 1, where you get 3, you know, you get other words, yeah, various stuff of different levels of interest. And if we look at the speech for episode 12 specifically, so just episode 12, and we plot it out, it's important to note actually that this vector is just going to be a bunch of 0s and 1s, monologues. This empty vector here is just going to be some 0s and 1s. And this is just because we're not overlaying all the podcasts in the series now. Now we're just specifically looking at episode 12. And we can see in the first 100 seconds, you know, the host introduces, maybe the guests introduce, they kind of talk back a little bit back and forth. We can take out the scope a little bit. You can see, wow, it's really like a back and forth conversation. So we have all this data. What's something interesting that we can do with it? And if we think about in the context, let's imagine this podcast has just had a ton of success in episode 12, and a sponsor approaches them and they go, hey, we want to put an ad in your podcast. Is there a good way we can do that algorithmically? And so the way I came up with in the broader context of my podcast research was to specifically look at when certain kinds of organizations are named in the podcast. Now, to do this, we load in the display transcript, so we get all the punctuation. We tokenize it out. We use the POS tag to flag out things like nouns and verbs and understand like the composition of the words that they're saying. We use this function anyChunk, which then organizes all of this stuff into a hierarchy. And with that hierarchy, we can actually call out specific things such as organization. Now, it's worth noting here, I'm using the natural language toolkit. Spacey is a pretty good alternative, but I figure we've looked at enough tools, so let's just keep it simple. And we can flag out some of the organizations that are mentioned in episode 12. And we see things like, okay, cool, a lot of basketball teams, like Geico, which is an American insurance provider, and a bunch of stuff like that. We even see like Yeti, which are like the cups. And it's pretty interesting, right? So we get a ton of these different organizations here. So what if like a more natural way of inserting ads into a podcast is rather than just like put them at the start, put them at the end, put them at the halfway mark, we looked for particular points where the host brought something up. Like maybe he was talking about Geico and he was like, oh yeah, like got in a car accident, Geico was great for my insurance, right? I believe it'd be a lot more compelling for then an ad to kind of like pop out for Geico at a natural point after that. So use the transcription to flag out this particular section. In this case, I'll use the target word, the Bucks. I'm not a Bucks fan, but we'll use the Bucks and we'll look at when they mention them, right? So they have this sentence here, who should, well, the Bucks should win though, right? And it starts, about 57 minutes in. Now, the interesting thing about this is like, well, we need to take context into account because if they're saying some like terrible things about the Bucks, we don't want to insert a Bucks ad right after. So what we can do is we can look at the sentiment of the sentences around when they bring up the Bucks. So we can see we take 3 sentences before they mention that and then 3 sentences after, and they kind of have different lengths of these sentences. And we can see that this negativity or the negative sentiment captured is below the average for the podcast, and the positive sentiment is above the average, which we calculated way back when we were just looking at transcriptions. So this suggests that in this point, they are talking like a little bit more favorably about these podcasts. So what we can do now is I can actually pull out the segment of audio here and we can give it a listen, and you can decide for yourself whether you think it is a good place to put an ad or a bad place to put an ad. Just got to navigate to 57 minutes here. Cool. Now let me know.
If the Suns lose, like, okay, so the Heat.
Marcelio, are you able to hear that audio when I play it like that?
Yeah, we are able to hear the audio you just played. Yeah.
Great. Thank you.
On Chris Paul, he the guy, right? So, question: who should the Bucks should win though, right? Of the teams left, I feel like the Bucks have the best case of like we should. You can talk yourself into. I think they have the best player left.
Yeah, if Kawhi were healthy, it would be different.
So we can see in this segment here, they're talking pretty favorably about it. They're in fact saying that the Bucks should be the one to win the competition, right? Now, this is probably a pretty good place to insert a Bucks ad. They're talking favorably about the Bucks. Maybe you have a viewer that doesn't have an NBA team. They're on the fence. They're trying to decide which one they support. This guy says the Bucks are going to win, and then you get an ad at a natural point after that says, hey, you want to buy Bucks tickets or you want to buy a Bucks jersey or come check out the Bucks website. you're going to probably be more likely to do that than if they just inserted that kind of arbitrarily into the podcast. Because if you trust the host and you like what he's saying and you think that he's right, well, then getting an ad for that is such a more compelling call to action than that ad just waiting till the end, for example. Now, the challenge here is inserting this like naturally into the flow of the conversation, right? If you do it just on the transcripts, well, you can throw it right in after a period, right? After a full stop. But that kind of can interrupt the flow of the conversation because it's a podcast. They're having this chat. They're jumping back and forth. It's a bit awkward if a Bucks ad just appears like midway through a conversation, interrupting at the end of someone's sentence. But at the same time, you don't want to wait too long. You want to be top of mind for the viewer. So you want to insert it at kind of a more natural point. Now, if we look at our data that we got from our speech analyze API, we can kind of see this point here. This right here is where the 10th speaker, which is the guest, the guy that you heard talking, is speaking about his stuff. Now, this is where he mentions the Bucks, right? And then this is like the following, like how much I got, the following 20 seconds after that. Now, there's a few different points here, but you can see the conversation keeps jumping back. I want to call out specifically, though, this section here, where there's a gap between the speakers. Now, if we have a closer look at this, we can actually see, and this is just us like checking who's speaking when or checking when speech is happening. We can actually see a few points where silence is occurring in the podcast. And again, silence is an audio defect. And that's what's happening in this segment here. There's a silence section where nobody is saying anything. Now, this is a pretty good indicator that the point has like finished or the conversation is kind of taking a more natural pause rather than just throwing it in at the end of a sentence. So in this little pause section here, what we can do is we can kill two birds with one stone. We can fix the silence section and insert an ad there. Because there's a silence section, it's probably a pretty good place for an advertisement. And if we look at this here, we can flag out a few silent sections that occur. This is 12 seconds after he says the Bucks are going to win, 39 seconds. And we see this nice segment here of 47 seconds to 48 seconds, which is probably a pretty compelling place to insert an ad. Cool. I'm going to switch back to the slides now. And that was a lot of code. And that was a lot of me talking at you. I just wanted to give everybody just a quick second to take a deep breath. I'm going to have a drink of water, and then we're going to move on. General reminder, you can still share your ideas and win API minutes. I really would look forward to seeing some cool ideas on there and want to make sure that we can get some resources to those ideas so they can maybe investigate this. So feel free, even if you feel like the idea is really simple or dumb. I think there's a lot of cool stuff you can do out there.
All right, so meanwhile, I'm going to read some of the comments from our participants. Well, Tom mentioned that it would be quite interesting to run it on comedian doing impressions, yeah. That would be, and they also mentioned about possible overlapping tracks in the podcasts, right? That was mentioned by Iya. Then Tom also mentioned that it would be curious to see how those packages are tested.
Yeah, well, so again, I'm not actually one of the engineers that builds these packages, so I can't give you a ton of insight into that. But if you reach out to me over Slack and you are really interested, I can put you in contact with some of the people that do work on that stuff, and they can give you a bit more of an in-depth explanation as to how these kinds of models are trained. Yeah, all right, we're kind of running out of time here, so I'm gonna keep going. Cool, so just to recap, we looked at common words, where these words occurred. We filtered out stopping words. We looked at like sentiment distributions throughout the podcast, to see maybe which episodes are kind of more negative or which ones are more positive based on the model that we're using. We looked at doing some clustering to see if we can find some natural divisions between certain kinds of podcasts, as well as looking at the relationship that those podcasts might have. We also had a look at these metrics that we used for that clustering kind of individually to show like kind of how distinct some of these differences can be. We looked at the composition by podcasts. So we could see like, oh, where are the audio defects, where, how much speech is in it, how much music is in it. And we also had a look at like all of the speakers as they're like, you know, going through their whole podcast thing. And we had to look at like some patterns, some macro level patterns that you can identify when you're looking at like 20 podcasts. You can see, well, there are kind of patterns to when people talk, and there's areas of higher intensity as well. And then we had a look at, you know, a specific use case in episode 12 where we tried to find a more natural way to insert ads. And we had a look at these talkers, and they're in a heated discussion. They're talking over each other a little bit, but we found a nice segment where it might be more relevant to insert an ad. Yeah, that's kind of what we've covered. And now I want to take a second to, since we do have some time, to have a look at some of the ideas everybody else has come up with. So please, if you haven't had a chance, go fill out that form. I definitely think people have some like cool ideas. Like don't be shy to share them. I won't say anybody's name, but we can kind of talk through like a few of the cool ideas, and maybe I can point out some parts in the data that might be a little relevant. Cool. So let's have a look at some of these ideas. So here's a pretty relevant idea, especially with like the transcription stuff, is to convert a particular like host or talker's notes into kind of like cliff notes almost, or like a summary of them in a way where you can see like, oh, like what guests were saying stuff and who were his key guests, and which guests were, you know, particularly relevant. Identify how often speakers interrupt. This is a funny one. I'd love to see that like in like a classroom setting or something like that, where people jump into calls, you know, without their microphones muted or whatever, and it kind of interrupts the flow of the conversation because somebody's almost like interrupting the virtual conference. So I like that idea. That'd be an interesting one. We also do stuff like analyze particular podcasts and try to pull out specifically, like we have all those speakers, which one is the host, and is he the host because he's saying things a certain way? Is he like talking about himself a lot? Is he taking the spotlight away from the guests? Is he doing some stuff like that? Yeah. And so those are a few of the ideas. Another one of the ideas, I like this one from Griffin. It is a podcast auto segment highlighter. And okay, I've got it. So it's like, I get this idea. I like this idea. This is cool, right? It's the idea that if you have a Twitch stream or a presentation, you know, or these streamers are like streaming games or whatever, there's obviously like segments of their like 3 or 4 hour live streams that are like highlights, right? And if there was a way that you could particularly like flag out the highlights by looking at like how there's talking and like loudness, I like that idea. That's a cool one. I can see how that's pretty related as well to like the idea of trying to determine the most intense part of a podcast. But that's kind of cool. And I can imagine that you build a tool that like automatically clips out these like segments of audio. So that's pretty cool. If anybody else has other ideas, like please submit them in the form, come back to it. We're looking to, you know, give away some minutes so that people can go and experiment with this stuff and do some of their own cool projects. I also want to leave a quick second here in case there are any other questions. Oh, I see some right here. Just one project idea, not necessarily. Feel free to go through and submit like as many times as you want. You know, like if you've got a cool idea or if you've got a bunch of ideas, just shoot them. I don't mind looking through them. And we keep track of your email, and we use the email to credit you. And we can also reach out and talk to you about your projects if you need help or have some interesting questions and stuff like that. Yeah.
I think one interesting question comes by Tom. He's asking about if the application is able to apply it for different languages, for foreign languages actually.
Yeah, so because the API works on the signals specifically, and it doesn't like convert it to a transcript and then run it on the transcript, it does, in theory, work for a bunch of different languages. In practice, English is kind of the most effective one, but that's not to say that it doesn't work on other languages. You can test out because it's working. It's not like it doesn't convert it into like a human language. It kind of does like what we were looking at with the PyAudio analysis package, where it pulls out like these signal-based features. And it has been tested on other languages, and it does work on other languages, but as a blanket statement, does it work on all foreign languages? It's hard for me to say. I don't know that one for sure. Any other questions?
Well, let's see. Does anybody have any other question? We still have like 5 minutes left. And please do not forget to go into the Dolby Web App in order to propose your ideas. I think these projects are quite interesting and would be applied in several fields and podcasts.
Yeah, absolutely. That's a good question for transcription. Depending on which transcription you're using, this can be different. In Azure, it provides a couple different versions. It provides like flat the words in order, which is the lexical that I kind of looked at the start for stuff like common word mentions. And then like it also provides examples where it attempts to insert punctuation. In practice, the punctuation it inserts is very basic. I don't think I've ever seen it use a like semicolon or a comma. It's mostly just full stops, question marks, exclamation marks. It's a good question. How does it recognize a question? That is a good question. I'm going to be honest, I actually have no idea how the transcription does that part. That'd be a good question for the people at Azure, I think. But I guess as well, it probably works on the signals in a similar way, again, to what we were looking at that PyAudio stuff. And maybe there's like a particular pattern in the signals that allows you to denote like a question or something like that in a particular language. I don't know.
There's another question which says, how about punctuation which is inserted versus punctuation is inserted? Punctuation
yeah, so I see what
versus punctuation is inserted. Yeah.
I see what Tom's getting at there. Is it like punctuation is inserted, or is it punctuation is inserted? I'm not 100% sure, but I think sometimes even human beings have this problem, right? Of like, sometimes people can even just say stuff and you're not sure whether it's like an actual question or whether they're just making a statement, like a rhetorical question. But that'd be an interesting question for the people over at Azure. Maybe a bit of Google investigation. If you want to chat about it some more, my details are included here, and this is open to everybody. If you want to reach out to me via Twitter, or my LinkedIn's pretty easy to find, Braden Riggs, and you want to chat about this stuff. I mean, I'm continuing to work on these projects, and it doesn't necessarily have to be Dolby related. I'm kind of just doing a lot of research in this space in general. So if you do want to have like conversations about it, please reach out. I love chatting about it. And of course, I can't cover everything in this whole workshop. Yeah. And if we've got no more questions, I just want to say thank you for everybody coming to this presentation. Of course, if you're interested in learning more about our APIs, please navigate over to our documentation, which is on screen right now. Or if you want to share more ideas, absolutely feel free to do so. Again, we're going to try and credit out a few people with some minutes so that they can maybe play around and try out their idea. Of course, like, you don't have to do it. We can just give you the minutes and you can go try it out. Like, there's no expectations or anything like that. It's totally your project. But if you do want some more minutes to maybe go do your own investigation, we're happy to help you out with that stuff. And we'd also love to get your feedback on this presentation. So please reach out to me via Slack or Twitter. And thank you for everybody watching. I hope everybody enjoys the rest of PyCon or PyData.
Thank you so much, Braden. I think your talk was quite interesting and constructive. Several tools applied. The algorithm was fully explained and also following several other example codes. So I think it became a really great experience for everybody. I also want to thank Tom, EL, which provided good feedback and somehow enriched this conversation. I think most of our participants are congratulating you. Like Olga, she says, great talk. EL, again, is thanking a lot, great material delivered. Just to keep it up. Good presentation by Ignacio Ruiz. We also have Jason, who is clapping for your presentation.
Well, thank you, everybody, for the feedback. Again, these samples are provided if you want to just go tinker around with it yourself. I'll also work at adding the slides to the same GitHub repo if you want to also have a quicker or closer look at the slides, I should say. Here, I'll repost that right there. And again, another call to action. If anybody is just an audio data enthusiast and wants to go contribute on the awesome audio, that's just open to anybody. Doesn't have to be related to any of the stuff that we are doing. Just has to be related to, you know, audio development and audio technology in general. So I'll share this link as well. Please, yeah, feel free to contribute and come join the awesome community that we're building around audio data.
All right. Thank you very much, everybody. We have to leave the room since other presentation might be started. Thank you very much, everybody. Thank you so much again, Braden. I hope we see you soon again.